Good morning, friends. So in the last two lectures, we started shearing stresses, and we studied distributions above the shear stress for rectangular sections and distributions above the shear stress for circular section. So today we'll see distributions above the shear stress distribution for I section. Consider this is the I section. Consider I section having overall width and depth are capital B and capital D. So this is overall width and this is capital D, and wave thickness THIC thickness and depth are small b and capital D. So this is small b depth, width, and this depth equal to small d. Now consider consider its neutral axis. So this is neutral axis, Ax. So this distance equal to d by 2 and this distance equal to small d by 2, and let level EF having distance y from neutral axis, EF in top flange. So you can consider this is for top flange. So this is which is shown in figure by shaded. So this is level EF. Now for top of flange, for top flange above level EF, shaded area equal to. So this level, this distance is the y. So that's why shaded area equal to. Now width multiplied by thickness. Width equal to capital B. Now thickness equal to total capital D by 2 minus y. This is clear because this is total, because we require this. So this is total D by 2 minus this y, and centroidal distance of shaded area from neutral axis. So this is equal to, now we are calculating this distance. So this distance equal to y bar. So this is y bar equal to, now capital D by 2 plus y divided by 2, because this is capital D by 2 and this is y divided by 2. So that's why AY bar equal to B into y, and this 2 D by 2 plus y. So this is B by 2, capital B by 2, D by 2 square. So this is D square and this is 4 minus y square. Right? Now shear stress at, so here's shear stress equal to, yes, A y bar. So at here this is top flange divided by BI. So S equal to, okay, this is tau. This is tau into capital B by 2 D square minus 4 small d square, y square B divided by I. So here's also, this is capital B. So this capital B will get cancelled, and this is S by 2I d square. Now if y equal to, means at the extreme fiber d by 2, y equal to d by 2, tau equal to 0, and if y equal to small d by 2, tau equal to S divided by 2I d square by 4 minus small d square by 4, or tau equal to S 8I d square. So this is nature of the, so nature of curve is parabolic because here's square. So that's why nature of the curve is parabolic. So after that, now shear stress consider this shear stress. This is B. Now this is shaded area. Now consider is parabolic. Now second case, shear stress distribution in the wave width of the section at a distance. So this distance let y from neutral axis. Now again this is capital B, this is total capital, means this is capital D by 2, this is small d by 2, and this is y bar. So that's why S equal to again S A y bar divided by bi, because width equal to b. No, sorry, this is tau equal to. Now, but A y bar is the momentum of the flange, area about the neutral axis plus moment of inertia plus moment of inertia of shaded area of the wave about neutral axis. Now momentum of the flange about the neutral axis. So this is width equal to b, depth equal to d by 2 plus, or this is minus small d by 2. So this is area, y bar equal to capital D by 2 plus small d by 2 divided by 2. Right? Plus now this shaded area, width equal to b, area m is equal to Now d by 2, small d by 2 minus, because this y, so this is depth multiplied by, so this is d by 2 plus y divided by 2. So this is correct. So that's why this is equal to a y bar equal to b capital B by 2 d square by 4 small d square by 4 plus so this is b by 2 again b divided by 2 capital small d square by 4 minus y square. Alright, now let y equal to, means this is at the junction, equal to d by 2. So y equal to d by 2. So this ay bar equal to b by 2 d square by 4 minus, and this second terms 0, and let y equal to 0, ay bar b by 2 d square by 4 d square by 4 plus b by 2 d square by 4. So that's why shear stress equal to, now by taking here commons, b by 8 d square plus b divided by 8, oh sorry, this is 2, again you can put d square by 4 square minus y square. So here's these steps you can take after that also. So multiplied by yes, and this is b divided by I. Okay, so we are calculating about shaded area, means this is B. So that's why this is b by 8 d square minus d square plus b divided by 8 d square divided by bi. This is at neutral axis. This is at neutral axis. So that's why the distributions of curve. So here's after that, because this is abrupt change, and so this is tau max. So this is tau max. So here suppose this is A point and this is B point. So that's why shear stress at A, that is just above the junction of wave and flange. So just junctions of wave and flange is here. So there this is so I erase that, but here's tau equal to, I think, yes into eight I. So this BB, so this is correct, and shear stress at B, that is just below, so means here just below of the junction of wave and flange. Now this is equal to tau into yes d square minus d square divided by into B divided by capital D square only this much is the difference. So here's this is the ratio. So try to understand this. So this B by capital B by B, rest of the things that will get cancelled. So only this much is the difference. So that's why this is the distribution slope of the shear stress. Now we'll see some of the problems because in the last in yesterday's solving of the problems, we consider shear stress equal to W by 2 for concentrated loads. So that's why for UDL. So UDL also we consider in the last two problems, UDL equal to, instead of the W Newton meters per meter, we consider that is Newton. So today we will see, because you may be confused. So that's why today again I solve yesterday's problem. Otherwise, message will be go in wrong way. So please note down a timber beam. So actually this problem is the yesterday's problem. A timber beam 200 mm wide, 200 mm wide and 150 mm depth. This is 100 mm wide and 150 mm depth, supports a UDL or a span of 2 meter. So if the stresses are, if the safe stresses are 28 Newton per mm squares and 2 Newton per mm squares in bending and shear. Calculate the maximum load. Calculate the maximum load that can be supported by the beam. By the beam. So in this case, this is simply supported beam and this length equal to 2 meter. Now suppose this is considered W in Newton. Let W in Newton over the span of 2 meter. So instead of the you means W, small w, means W means that we have to convert W into L's. So we are considering this is capital W. and this is unit is over the span of the 2 meters. So that's why now this W is shared by two supports, RA equal to W by 2, RB equal to W by 2, because this loads supported by two supports, RA equal to W by 2 and RB equal to W by 2. Now this is W load, so that's why bending moment equal to, now this W by 2 force multiplied by this distance L by 2. So this is force and this is distance. This is force and this is distance, because we consider this is in Newton, minus now UDL, this is W into so this is W divided by half, because this is half, and this is L by 4, because this center distance, this distance equal to L by 4. So that's why this is WL by 4 minus WL by 8. So this is equal to WL by 8. This is clear? Now by using a relation sigma B divided by Y equal to M divided by I. So sigma B M equal to by 8 multiplied by Y equal to, so this is 100 and this is 150. So that's why this is 150 divided by 2 and this is 100 into 150 cube divided by 12. The sigma B equal to, so this will get cancelled, W L so this is 6 multiplied by 6 and this is 8 into 100 into 150. Now this length and this is in meter, so that's why put W into 2 into 6 into 1000 and divided by 8 into 100 into 150 square, and the sigma B equal to 28. So W equal to 28 into 8 multiplied by 100 multiplied by 150 square divided by 1000 divided by 6 and divided by 2. So this is equal to 42,000 Newton, or W equal to 40 or 42 kilo Newton. So this is try to understand. Now by using relation shear force maximum shear stress equal to 3 by 2, and this is average shear stress. So tau max equal to, this is given, maximum shear stress 2, 3 by 2 into S divided by, I think, B into D. So this is 2, 3 by 2. Now W equal, S equal to shear force equal to maximum shear force equal to W by 2. So this is W by 2, B equal to 100 and depth equal to 150. So W equal to, this is 8 multiplied by 100 into 150 divided by 3. So we'll check. 8 into 100 multiplied by 150 divided by 3. So 40,000. W equal to 40,000 Newton load. Calculate the maximum load that can be supported by the beam. Supported by the beam means the maximum load that can be supported equal to, so this is W, this is 40,000 and this is 42, so that's why 40,000, because this is divided by 2 equal to 20,000 Newton or 20 kilo Newton. W equal to so this is not W, so this is a reaction, and safe load UDL equal to 40 kilonewton. For 2 meter length. So this is for 2 meter length, and this may be 20 kilonewton per meter. So why this is 20 kilonewton? Because this is 20 divided by 2, 40 divided by 2. So this becomes UDL, means this is small. This is small. Try to understand this. This is small W, this is kilonewton per meters, and this is capital W. Otherwise, because I consider in the yesterday's problems, this is capital W. So that's why I explained this. Otherwise, because in the shear stress, I use this relations S equal to W by 2. I used that times W by 2. Otherwise, here we have to use WL by 2. So I think you understand yesterday's problems clearly. Now we'll see another problems. A simply supported wooden beam
simply supported wooden beam of span
1.3 meters,
having a
cross section
150 mm wide
and
250 mm deep, carries
a concentrated load
W at the
center
allowable
working stress
R sigma B equal to 7 Newton per mm squares and tau equal to, so this is bending and tau equal to 1 and shear
what is safe load?
W.
So in this problem, this is concentrated load given, so no problem.
Simply supported wooden beam 1.3 meter. So this is length equal to, suppose this is A, B and this is W. So this is 0.65 and this is 0.65 meter, right? This is 150 and this is 250. A point and this is B point. So RA and this is RB. So RA equal to W by 2, RB equal to,
Because at the center means
this is W by 2.
now
Moment maximum equal to W by 2 into 0.65 multiplied by 1000. this is 500. All right. Multiplied by 0.65. So this is 325 W. This is in Newton mm. Right. Now sigma B m divided by y. Sigma B equal to m by y divided by I. So this is m into y equal to d by 2, and this is BD cube divided by 12. So I written this is general formula. So m into 6, and this one d will get cancelled, BD square. 6 multiplied by m BD square. Now this sigma B equal to 7 6 into 325 W, B equal to 150, and this is 250 square. W equal to 7 into 150 into 250 square divided by 325 divided by 6. 33.653 kilonewton. 653 Newton, or 33.65 kilo Newton. So which is maximum, which is lower, that we can consider by considering shear stress. So again, tau max equal to relations 3 by 2. This is average shear stress. This is equal to 1 and 3 by 2. S equal to, so this is S divided by BD, 3 by 2, and this is W by 2 into BD. So W equal to 4 by 3 multiplied by BD. B equal to 150, right? And this is 250. W equal to 4 multiplied by 150, 250 divided by 3. This is equal to, W equal to 50,000 Newton, or W equal to 50 kilonewton. So that's why W equal to, and this is also W. So safe load which is lesser, that is to be considered 33.65 kilo Newton. This is your expected answer, because this load is the more. So as per the considerations about the shear stress, 50 kilo Newton load is more, and this is 33.65. This is the safe load. So that's why safe load can be applied 33.65 kilonewtons only. So that's why today we will stop here, and in the next class we will see the distributions of the shear stress for. So this section means here likewise about neutral axis. So this is equal to 1 Newton per m square. Tau max equal to.
So in the next class we will see for the different section. So that section may be I section, T sections, or some of the irregular sections, means unsymmetrical sections about neutral axis. So we will see such type of the problems in the next few classes, and after that we can complete these chapters and we can start 5th unit. So I think in the 5th unit is the torsion chapters, or torsions and column and strut. So we will see in the next week. So that's why today I stop here and we will continue sharing distribution stress. So in the next lectures I first explain so what are the different shear stress distributions for what is the shape of the shear stress distributions for different sections. That first I explains in the next lectures, and after that we can solve the problems related with the shearing stress for the different cross sections. So that's why today stop here. Thank you.